Alright, you guys, new chapter. We're in chapter 4.1, and what we're actually going to be doing is starting to build our, we're going to try to go back to college algebra. Alright, and what I mean by that is that in college algebra, what we usually had is we had a function. That function depended on x, and our output was y. And we've kind of stepped away from that because what we've been dealing with so far, using our unit circle to kind of as a ending point, is that our functions, let's just stick with the big two, sine and cosine, right? So the sine, we usually take the sine of an angle, and then its output is dependent on, right, y and r, and then the cosine of theta is depending on x and r, and even the tangent of theta is dependent on y over x. So we've been using the x and y coordinates along the edge of the terminal side of an angle, right? That's what we have there. We've been using those as our outputs. And as we've slowly built from our XYR definition to our right triangle definition and then to our circular definition, right, where we just change theta, right, r is equal to 1, so theta and the arc length along the edge are the same. So we can, interchange the theta for s, and we still have the same ratios. So our input so far for our functions have been either the angle of rotation or the arc length along the edge. Depending on what function we use, sine, cosine, tangent, or one of their reciprocals, there's some ratio between y, r, and x. And of course, when r is equal to 1, sine is just y. When r is equal to 1, cosine is just x, as we've been using so far at the end of there in chapter 3. So that's where we're currently at. But to go back to the college algebra-ness of this, what we need to do, right, is just kind of be a little fast and loose, if you would, with the variables. What I'll do is to initially sketch these functions, what I'll do is we'll continue to think in terms of theta or s, and then we'll slowly build up to there. Because right now, what we've found, right, it doesn't have, it's also an angle of rotation, or it's an arc length, but with applications, we can find that we can take the sine, the cosine, the tangent of anything, a time value, any real value. It just doesn't have to be stuck to a right triangle. So here's how we're going to start doing that. What we're going to do, so we can get to the college algebra-ness of this, is we'd like, right, for x to be along the x-axis, y to be along the y-axis, and then we had some function, right, some function called f of x. And then we can analyze it. It passes the vertical line test. We can look at its inverse. We can see where it's increasing, where it's decreasing, all its high points, all its low points. So we'd like to, right, be able to analyze a sine, a cosine, and a tangent graph with respect to that. And right now we don't have that because we've been stuck just rotating around a unit circle, and then using that unit circle to come up with our sine, cosine, tangent value. So this is where we want to head to, and we're kind of limited by that. And the other thing that we're going to end up doing is when we do put things along the x-axis, right, we're going to either, we can call it theta or we can call it s, and this would basically be the output of that, right, so just kind of getting us ready for that transition. And then the other thing that comes into play is we don't want to use degrees, right, because if we use degrees to do one full rotation, I'd have to go from 0 to 360, and even in our graphing calculators, right, our standard viewing rectangles usually from -10 to 10, -10 to 10. So we'd really have to play around with our x min and x max just to get a full rotation, right, along the x-axis for a sine or cosine or tangent graph. So we actually want to work in Radian mode. And that's going to be a challenge, and hopefully I've prepared you guys for that, because we need to be really good with our fractional uses of pi. So we don't want to break things up in terms of 1, 2, and 3 all the way to 360. We want to break things up in things like pi over 2 and pi and 3 pi over 2 all the way to 2 pi, because 2 pi is roughly about 6.28, and that fits very nicely in our standard viewing rectangle in our calculator. So when we go into this college algebra view, right, it turns out that what we normally like to have, right, is to be in Radian mode. So that's how we usually like to do that. And here's how we basically do it. So again, as all graphs do, as my 150 students and my 120 students are learning, right, it's all about finding solution points, right? All the solution points along the graph. And so we usually do that by finding a table of values. And so let's go ahead and let x be x right now. And let's let y, right, equal, how about we do the sine of x first? And what I'm going to do is use all the really nice angles, all the things that deal with the quadrants, right? So basically our quadrantal angles, and then I'll fill in some of the details as we go along. So if we do the quadrantal angles, it starts at 0, right? And then we have pi over 2 coming along. I'm leaving some space for some other angles. And then we have pi, and then we have 3 pi over 2, and then we basically end back at 2 pi. All right, and so as we move around the circle, and then what's nice about coming back to 2 pi is we're right back at the beginning. And so when I start putting those values in, right, we already know just from the unit circle, the sine of 0 is 0. The sine of pi over 2 is 1, right, the y value. The sine of pi is 0. The sine of 3 pi over 2 we know to be -1. And the sine of 2 pi, right, is going to give us 0. So again, I'm taking the sine of 0, the sine of pi over 2, the sine of pi, the sine of 3 pi over 2, respectively. And just using my unit circle and taking account all the y values at each one of those locations. So just with that alone, we can come up with a pretty decent sketch, right? So here's x along the x-axis. Again, my scale is pi over 2, pi, 3 pi over 2, and all the way out to 2 pi, right? And we could go on forever if we want. And just graphing the points that we have, right, we have 0, 0, pi over 2 occurs at 1, pi occurs at 0, 3 pi over 2 is occurring at -1, and 2 pi occurs at 0. And so you can start to see pretty much a wave. Filling in one of the details, how about we just go halfway between 0 and pi over 2? Well, that's pi over 4, 45 degrees. What do we know about the sine of that? Well, using our unit circle, right, that's the square root of 2 over 2, which is roughly about 0.707. What about 3 pi over 4, right, over here in quad number 3? Well, we're still the square root of 2 over 2, which is roughly about 707. What about 5 pi over 4, which puts us down here in quad 4? Well, we're negative square roots of 2. Or negative 0.707. And then here that we would be looking at 7 pi over 4. So that would take us about right there. And we're negative square roots of 2 over 2, which is negative 0.707. So if we fill in those other details, what we basically have, right, pi over 4, so we're about, there's a half, so we're a little bit over half. At 3 pi over 4, we're that same value. And then at 5 pi over 4, we're negative of that value, and then we're negative. So when you start filling in all those details, what you basically have, right, is what our sine graph looks like over one full rotation. All right, and that's a classic case. And the major points, right, are the intercepts, right, 0, 0, pi over 4, and 2 pi over 0. And then the high points, right? We have basically a relative max at pi over 2, 1, and a relative min basically at 3 pi over 2. And because of the idea of coterminality, if we were to keep extending this out, this graph would continue going along the same wave. Even back, right? It would go along the same wave. So out up here, we'd end up at 4 pi, and I think that would be at 3 pi. And so we now also have this idea of a period. The period is 2 pi, right? And this is also 2 pi. So over a series of 4 pi, I've gone 2 cycles. Or back to the unit circle, we've gone around twice. And so here's one full rotation, here's the second full rotation. And I'll talk more about that period stuff in a moment. But there's basically our graph of sine of x. And that's important for us because now that I have a kind of a college algebra view of it, right, we can do things with this graph. We can shift it to the left. We can shift it to the right. We can shift it up. We can shift it down. We can compress it. We can stretch it. So we can do all those college algebra transformations. And that's pretty much what happens throughout 4.1 and 4.2. But right now, let's just focus just on the graph. And there's basically how we graph sine. And this is the most famous part right there, over 0 to 2 pi. If you can commit that to memory, commit these 5 points to memory, you're going to help yourself out a lot as we transform them. I can already see we're 10 minutes into this, so how about I do cosine, right, on another separate video. And I'll see you guys in a moment for that.